Welcome. In this session in linear data analysis, we'll explore how to approximate a matrix by a rank K matrix. So let's suppose that our matrix A has all real numbers and it has m rows and n columns. And what we want to know is how can we approximate it? Well, we can approximate with a matrix, let's call it C, and it will also have all real entries, and it will also have m rows and n columns. And so we can measure this by saying, what is the matrix norm of A minus C? And now we need restrictions on C. So let's consider a simple case. Let's consider that the rank of C is 1. And how could we represent C? So we can build this. So build C, and we could use some matrix Z that has all real entries and that has m entries. And so we could say C equals, well, I could say that that is some alpha 1 times this construction vector, alpha 2 times this construction vector, and so on until I have all of the columns of it represented, and each one of these columns is the same vector. So this has rank 1 if Z is non-zero, because each of these columns is a scalar multiple of some other column. So how could I write that? Well, I could write that as the column matrix times this alpha transposed. So now let's try this. Let's consider an alternative. And this alternative is a very simple modification. Okay? Let's say we want to use a vector W that has a vector norm of 1. And let's say that our vector alpha is some multiple, some scalar multiple of W. And we can interconvert. That is, if you give me an alpha, then I could take the norm of alpha and I could set that to equal beta, and then I could divide alpha, each entry of alpha by the norm of it, by the norm of alpha, and I would get W. Well, that's how we were building orthonormal bases in previous sessions. So we know how to intertranslate between those two. So that's not a problem. So now our rank 1 matrix looks like this. It is some column times some value times the transpose of some unit vector. So I could even say now that Z is a unit vector. Now the question is, what is the best choice? So, what are optimal values? Optimal values of this constructor vector, this scalar, and this W vector. Well, it turns out that if we use, so with either the L2 or the Frobenius norm, the optimal choice is we take the singular value decomposition of our original matrix, and the optimal choice is that we use C as we take the first left singular vector, U1, we take the singular value, sigma 1, and we take the first right singular vector and transpose it. And this is a rank 1 matrix because this is just U1, and the first column is U1 times sigma 1 times V11 times V1, etc., etc., etc. So this is a rank 1 matrix, and it turns out that that is the optimum. So now let's do a really, really big consider. So let's consider, write A as, let's write it as C1 plus C2 and so on up until the rank of A. And we'll say that C sub I is, we'll define that for this purpose as being the ith left singular vector times the ith singular value times the transpose of the ith right singular vector. And so this Ci will be. Now, how can I do that? Well, in a previous session, I showed you how you could take a matrix A and you could represent it as the sum of rank 1 matrices by using a singular value decomposition. Now we're going to do what Professor Jacobi says, invert, always invert. He doesn't mean that your original idea was wrong. He means that taking a different point of view may be valuable. So now I can represent A as a sum. And if I represent A as a sum of rank 1 matrices, each rank 1 matrix coming from the singular value decomposition of A, then this is an old and not very often used theorem in linear algebra, the Eckart-Young theorem, says that for the L2 or the Frobenius norm, this doesn't happen for everything, the optimal rank K approximation to A is C1 from the singular value decomposition plus C2 from the singular value decomposition, and so on until we get to CK. So let's make another observation here. Let's observe. Observe what is the column space of, let's say, C1 plus C2. Let's make it nice and simple, right? So what's the column space of that? Well, this matrix is U1 times U1 propagated plus U2 propagated, and so the column space of this, well, we could take the SVD of this, right? And if we took the SVD of this, it would turn out that it has to be the same thing, right? It has to be the SVD. We have to be able to write it in this way, and so we can either read out the series from the SVD or read out the SVD from the series. And if I read out the SVD from the series, then it is a vector space U with a double barrel, which is spanned by U1 and U2. And so what is happening is that a rank K approximation of A is, and let's underline this, is also a rank K approximation of the column space of our matrix A. So these are the same thing. As I try to approximate the matrix A using K of these rank 1 matrices, I am doing a rank K approximation of the column space of A. So let's recall a matrix that we had previously. One that we explored when we started looking at applications of the SVD was 1, -1, 2, and it was -1, 1, 2.02. And if we did a rank 1 approximation to this, the rank 1 approximation would be 1 -1, 2, -1, 1, 2. Oh, sorry, there was a minus sign here. So a rank 1 approximation almost gives us this matrix, and so we can say that the effective rank of that matrix is 1. So in practice, when do we stop?